we're supposed to have V, odd symplectic. It could be a manifold, but I'll just say vector space for now. Of fields, some functional on V, and you want that this equation is satisfied. And the example, the main example, V looks like this, and it's the derived critical locus of a functional S0 on some quotient. And everything is treated in the derived way. And in this case, the action S equals SPV encodes S0 plus gauge symmetry and this Poisson bracket with S is, well, any derived gadget is kind of differential graded as a differential squared 0 is a natural differential. And this complex this computes functions on the critical locus of S0. So in this example, the example when it actually comes from gauge symmetry, the classical master equation holds automatically. Okay, so just to remind you, I know this is the BV setting gets a bit involved, so I want to make sure everybody's reasonably happy.
You said vector space, but V doesn't have to be a vector space.
Yeah, we're working locally. V doesn't have to be a vector space. It should just be some odd. You know, if you were like a very fancy mathematician, you'd say shifted symplectic derived stack.
And in what situations does the classical master equation not hold automatically?
Well,
my question makes sense.
yeah, I mean, you could just write down some odd symplectic manifold with some random function on it. That probably won't be meaningful.
Right. But in what cases do you say, like, here's something I think is like a BV field theory I'm interested in, but I'm not sure, I need to check something?
Yeah. Well, the cases where you there are cases you have to do some work, and those are the cases when, like in this case, you don't have to do any work because we have an honestly invariant action. You have a group action on a manifold and a function on the manifold, and that function is just literally invariant. But what if it was a more complicated situation? What if my group only acted on the critical locus and not on the manifold itself? Then you'd have to think about homotopy coherences, and this BV action functional you get would be much more complicated, and it would have terms which are quadratic here and here, which are the higher homotopies saying that the saying that the action is sensible on the critical locus, but not on the whole manifold. That happens in supergravity, because in supersymmetry, what you find, say, in high dimensions, the supersymmetry says your fields have some action over Lie algebra, but actually the the commutation relations of the Lie algebra only hold once you impose the equations of motion. So if you wanted to turn the action of that supersymmetry Lie algebra into a gauge symmetry, you wouldn't be in this simple situation. You'd be in the much more complicated situation where your gauge symmetry only acted on the derived critical limits and not on the space of fields of homogeneity. That's one of the reasons why supergravity is a giant mess. So there's a couple of things I wanted to do today. So firstly, I wanted to talk about the quantum master equation. So to talk about the way people normally talk about the quantum master equation is they choose coordinates, they assume V is a vector space, and then they write down some operator delta. So I'm going to take that approach. There's a more abstract approach in the literature where one should take V to be an arbitrary manifold, but then S to be a half density. And I'm not going to use that approach. So if we choose Darboux coordinates, xi and say theta I on V, where xi is even, theta I is odd, and these satisfy the canonical and anti-commutation relations. So then we can write an operator delta to be V Laplacian, which is e by the xi, e by the eta. And you can check that this is independent of the choice of coordinates. Of the basis, to be precise. So this does depend on the fact that I've if I take an abstract manifold, this depends on the fact I've written it as a linear space. And we're not going to worry about that. As I said, if you are worried about that, there's some literature dealing with this which tells you that in the nonlinear setting, there is such a canonical operator, but it doesn't act on functions, it acts on half densities. So then, we say that S satisfies the quantum master equation if this equation holds. So let's explain the meaning of this. So we suppose we're in a gauge theory situation, like here. So then, so I can look at V less than or equal to 0, which in the gauge theory situation consists of G in degree minus 1 and W in degree 0. Now, functions on V with the differential H bar delta, well, we already know what this is. this is, when we introduced the BV Laplacian, we saw that this was the differential, which gives you the divergence of a vector field and of higher things. So this is the divergence complex for the Lebesgue measure on B less than or equal to 0, and viewed as a linear space. Now, we can ask, what if we look at, we include so if we remember that this bracketing with S has as one of its, it has a bunch of terms. Some of them are enforcing gauge invariance, and some of them are enforcing the equations of motion. So if we add on this piece, this should be the divergence complex for the measure e to the S0 over h bar times the Lebesgue measure on this kind of derived quotient. But it can happen that this just doesn't make sense. Suppose G acts on W in a very nonlinear way, and the Lebesgue measure is not G invariant. It could be that there are no invariant measures. So it's not guaranteed that this thing will be a sensible cochain complex, just because there might not be any measure. So the quantum master equation is just the statement that this divergence complex is a cochain complex. Now, when we think about integrating in the homological way, having a divergence complex is really the same thing as being able to integrate. So we should think that the quantum master equation is really telling us there is a sensible functional measure. Questions about this? Yeah.
So I always thought that that equation is equivalent to like that equals a constant.
Well, because that's odd, and we're working over the base ring with no odd constants.
Oh, I see. Okay, then.
You're absolutely right.
Yeah.
If you're working over if you're working over some DG base ring, then that would be a good point.
I see.
So let's just to be concrete, trying to understand what this equation means when we take S to be, we have some linear action of a Lie algebra on a vector space. The vector space has a function on it. Maybe even the function is 0. What does this equation look like? Okay, so suppose G is a Lie algebra. G acts on W linearly, and we'll take the G invariant function S0 on W, just to be the simplest case, S0 is 0. Then we can ask, does the quantum master equation hold? Well, so let's write out our space of fields. Because then functionals on these fields have these names, C, X, eta, and B. These are the C ghost and the B ghost. And the BV action looks like half C squared plus CXE. This encodes the Lie bracket on G, and this encodes the action of the Lie algebra on W. Well, so what's the BV Laplacian? Well, maybe let's write it out more explicitly. If we are going to choose a basis of my Lie algebra, so these are the structure constants of the Lie algebra, and these describe the action of the Lie algebra on that vector space. So the BV Laplacian is delta is sum So B gets paired with C, and X gets paired with eta. So we want to apply this to this. And I'm hoping we'll see that there's a nice answer. So it's automatically true that S is equal to 0. This is automatic. So we want to check what del S is. So we apply the BV Laplacian to these two terms. So we get the first term, I'll contract a B with a C, and I'm left with a C. So I'll get something like half CB, C, B, F, I got my indices backwards. Anyway. So I'm taking a trace of the structure constants of the Lie algebra. And if I'm doing this correctly, this second term will appear with a different sign. Maybe I mix the signs up. The signs should be different. And the second term, I'm going to contract those two guys. CB, rho, B, I. So if we've done this right, and fix all the constants correctly, this is the trace. I'm being very sloppy, as you can see. This is the trace of an action. Okay, take a Lie algebra element, B, in the adjoint representation minus the trace in this representation. Okay? If this is a good thing, so the quantum master equation says that this should be 0. So what does this measure? If I have a Lie algebra action on a linear space, the trace measures how much the volume of this space dilates. This is, does TB changes the volume form W. This guy is how TB changes the vol on D, and they come with opposite signs because one is even and one is odd. So it really looks like the classical master equation, the quantum master equation tells us something about there being an invariant measure. Now typically, G is simple, this will always be true. If G is semi-simple, G has some abelian factors, well, this will always be true, but this may not be, because the abelian factors can dilate. This is not going to hold. Okay. Any questions? And it turns out, even if we include the term S0, nothing will change, because that will not be hit by the BB Laplacian, because it only depends on the x's. So that won't add on any other terms. So I want to discuss two other things in the finite dimensional case. I'm afraid we might not get to infinite dimensionals this week. So again, if V is odd symplectic, and S satisfies the classical master equation, then we can take, if I have some function t of degree -1, then I can do a transformation where I send S to S plus epsilon t. S plus epsilon S brackets with t. This still satisfies the classical master equation. And we should view this, if we do a transformation like this, we should view this as not really having done anything. This is just a change of coordinates. Of the Hamiltonian vector field. So, two actions which are related by these kinds of changes of coordinates, should be viewed as being equivalent. So if we have a first order deformation, S goes to S plus epsilon S prime. This satisfies classical master equation if S prime is equal to 0. Just because we're dropping the quadratic terms in epsilon. So the space of first order deformations modulo those which are those which just come from changes of coordinates, those which should be viewed as trivial. Well, what's that? That's the zeroth cohomology, the space of functions on V. It's differential. Because we want an element, S prime of degree 0, in the kernel of this operator, modulo things which look like that, because those are the ones that come from changes of coordinates. So when we study field theory, we'll often be, you can often look at complex, you might want to study what are the possible deformations of my field theory that are really physical, not just given by changes of coordinates, given by some cohomology group like this.
So I'm used to deformations of things being the second functional cohomology or something.
Uh-huh.
Is this that?
Well, yeah, good question. Well, when you said Hochschild cohomology, you had in mind an associative algebra. But if it was some other type of algebra, like an E2 algebra, we would have had a different. So let's look at the analog of this for associative algebras. So then we have, instead of this kind of boson bracket of degree 1, we'd have some bracket of degree 0. And because we're assuming it's non-degenerate, it will be something like a Weyl algebra. Now, then this is very like that because for anything with a non-degenerate bracket, like a Weyl algebra, every deformation is inner. So this would be like H1 of the algebra. And here we're seeing H0 just because it's different shift. What else? So at the quantum level, if S satisfies quantum master equation, then changes of coordinate act by S goes to S plus epsilon, S brackets T plus H bar del T. So the del comes because this is the action. We're looking at how does this vector field change. How does this vector field act on the measure e to the S over H bar this little Lebesgue measure? So if I act by this vector field on this measure, I'll pick up a term where I act on this function. That's that term. And I'll pick up another term what acts on the background measure, or Lebesgue measure, and that's that term. So then deformations look like and probably, maybe if you want, everything here can depend on H bar. So I only wanted to go through this quickly because the thing I really wanted to talk about like the other finite dimensional thing I really wanted to explain is gauge fixing. Yeah?
So I think I'm used to thinking that even in the quantum case, the deformations are governed by the class of that cohomology.
That's right. Well, there's a spectral sequence. So this guy has a filtration by powers of h bar, and the only, in practice, the only way you could actually compute this is by using that spectral sequence. So that the higher order terms are very hard to control in actual field theory.
So you're saying, so basically, that statement is if you kind of go order by order in H bar.
Yeah.
And each order, you solve, you get
Exactly.
that root and modulo.
Yes.
So you have to cancel off high.
Yeah, exactly. If you're working order by order in H bar, is it's the same as looking at the first page of that spectral sequence. But if you wanted to do, and then you would at each order, you would get that, because this term would move you from one order to the next. But if you wanted to do the whole thing uniformly, you would have this complex. But the reason, in practice, if you're doing field theory, we tend not to use this one and use the one order by order in H bar, is that this cohomology can be very difficult to compute. So you only know really how to compute it using that spectral sequence. So now we understand the quantum master equation to some degree. So suppose we wanted to actually use this formalism to perform an integral. So let's suppose that V is, as usual, looks like V W star with V2, and the action functional is the usual BV action functional associated to a G invariant function as 0 on W. The original integral that we would want to perform would be over the quotient of W by G. So this is modeled homologically by these pieces of degrees less than 0. Now, we notice that the original action functional just on W and the BV action functional agree when I restrict them to this subspace, things in degrees -1 and 0. That's because the BV action functional, the other terms we've added on, always depend on either the antifields or the antifields of the ghosts. Now, this integral will be problematic because it's not a Gaussian integral, because the quadratic term of this functional is guaranteed to have a very many degenerate directions just by virtue of gauge symmetry. So in the BV formalism, this is solved in a really kind of beautiful way. So what you find is that, well, you notice that this is the stuff in degrees less than or equal to 0 is half-dimensional subspace on which the symplectic form vanishes. So it's a Lagrangian. What you find is that you can do this integral here over any Lagrangian, and you will get, it will not change if I perturb the Lagrangian. So that I can do the integral by perturbing this Lagrangian a little bit, so that the action function is non-degenerate, and the answer is independent of the perturbation. Okay? So let me briefly explain why that's true. I'll explain why this is true for linear Lagrangians, just for simplicity. Suppose if I have some family of linear Lagrangians in V, then integral ds over h bar is independent of t if S satisfies the quantum master equation. So, as an aside, like from the point of view of derived algebraic geometry, this is slightly funny and a bit unnatural because these L's will never be DG subskeins. The reason being, well, if you want the quadratic term to be non-degenerate, that forces them not to be maximally far from being DG subskeins. So maybe we can suspend our belief in derived algebraic geometry for a few minutes.
Sorry, but why can't, like, if V was, like, say, T star of A1,
Yeah.
then I can't just take, that's not a, it's an odd, sorry.
Let's see, did I say that right? Maybe
Yes.
let me write the proof of the lemma because it's very simple. Well, so here's the proof. We take B L0 plus L star 0 x 1. So it's the shifted cotangent model of L0. Now, we'll assume LT obtained as the graph of a quadratic function ft on L0. So this is always true whenever in ordinary symplectic geometry, I'm very a linear Lagrangian to a new linear Lagrangian is always given by the graph quadratic function base. And it's true in the derived setting too, where ft is of degree -1. So to compute the integral, so to check that the whole result is independent of t, it really only matters, I want to compute the derivative, and since 0 could have been any point in the parameter space, I'm going to compute the derivative at 0. So ft is equal to t times f plus ot squared. And I'm going to just work to first order in t. Now, saying that it's obtained the graph of this function, another way to say that is that LT is obtained by applying the Hamiltonian transformation generated by ft to L0. So in ordinary symplectic geometry, I think this should be familiar. If I have a Lagrangian in a symplectic vector space, I can always, when I move it a little bit, there's always some Hamiltonian transformation which does that for you, and that's given by the function whose graph gives you the new Lagrangian. So what we can do is say, instead of changing the Lagrangian, we can keep the Lagrangian the same and apply this transformation to the integral. That will give us the same answer. So the integral is equal to the integral over my original guy times the transformation the Hamiltonian vector field associated with this function. And I'm just writing down the order t term, because the higher order terms involve exponentiating this transformation. And now we know what this transformation does to this measure. So that's integral over L0 of t times SF plus t over h bar times del f. And now we're done, because this whole thing, this is a divergence. So that's the idea. The idea is like this complex here is the divergence complex for the measure on L0. So another way to say it, so that the fact that the integral of the Lagrangian doesn't change if I change the Lagrangian is the same thing as the fact that the integral kills things which are in the image of the BV differential. Okay, thoughts, questions?
Where did we use that as satisfied with quantum answer?
Should be an extra term. V acting on. Actually,
What's that?
I thought that maybe the V acting on this measure also produces that's not
I think, no, let's, yeah, we use it as follows. I actually went too quickly. You're right. So we don't know this is a divergence yet. So this is the integral of the BV Laplacian, the h bar times the BV Laplacian, applied to e to the s over h bar 1 plus tf plus o squared. So this is obviously a divergence, because this is just the divergence for the flat Lebesgue measure. But to identify this and this, we use quantum master equation. Because if I apply the BV Laplacian to here, one of the terms, I'll get a term where I get this thing, and I'll get another term. So this thing minus the integral of Tf times half SS plus H bar downwards. So the BV Laplacian applied to this guy produces these terms. As these vanish, this thing is equal to that. It's a divergence. Is that better? Yeah. Any other questions? So if everybody's okay with like these ideas that the gauge fix we choose a Lagrangian, quantum master equation says it's independent of what Lagrangian we choose, and so on. I want to move on to trying to discuss the infinite dimensional case and why there are problems with the BV, why the quantum master equation has UV divergences, which is to be expected. I mean, the quantum master equation is saying it's about, does gauge symmetry preserve the measure? In infinite dimensions, there is no measure on the infinite dimensional space. So asking this question is, of course, going to lead to problems. So the first example we'll choose is Chern-Simons theory. So if M is a 3-manifold, recall that the Chern-Simons action fundamental field is a gauge field in M. Given by this expression. This is invariant under small gauge transformations, so we can apply the BV formalism. And if we do that, so the fields in the BV formalism are, well, in degree 0, we have the fields we started with. In degree 1, we have the antifields. So the thing that pairs naturally with the 1 form is a 2 form. In degree -1, we have the ghosts. And in degree 2, we have the antifields to the ghosts, which are 3 forms because they pair naturally with 0 forms. So it's a particularly nice thing about Chern-Simons theory is that the fields and antifields arrange into just the RAM complex of the manifold. So I'll use the symbol curly E often to write the space of fields. And this symbol of 1, square brackets, is there to say that we're shifting the grading. When we look at the forms, we normally would say 0 forms are in degree 0 and 1 forms are in degree 1. But this symbol shifts the grading down, so 1 forms are in degree 0. So another great thing about Chern-Simons theory is that you can take this action and look at the gauge symmetry and try to calculate what the action in the BV formalism is by having all the terms of how the ghosts act on the fields and so on. But if you do that, you will get something which looks strikingly similar to this at the end. So it has a very nice... So the full BV action is the same thing. So if I take a field, then the BV action So, does this make sense to you guys at all? I know many people have seen this before, but so what does this mean? We can expand alpha out into various terms. When these are forms of various invariant degree. And if I take this BV action and I write it in this expansion, it will have a term which is the Chern-Simons action applied to my original gauge field, which is in 1 form, plus a term which looks like, for example, there'll be a term where I take alpha 0 and alpha 2, because alpha 0 pairs with alpha 2 to give you a 3 form. And if you collect all of these terms, you will recognize the terms in the standard BV Lagrangian. So this term is the half C squared B term, because the 0 form is the ghost, and the 3 form is the antifield of the ghost. This term here, well, alpha 2 is the antifield to the gauge field. Sorry, yeah, alpha 2 is the antifield to the gauge field. So this is a term that tells us that about the gauge transformations of the gauge field. So this term tells us that one of the ways in which the gauge field transforms is A goes to A plus B. There'll also be a term, I'll write it here, alpha 0, alpha 1, alpha 2. This term tells us about A goes to A plus A chi, the other term in the transformation, and so on. So it's kind of a fun and slightly tedious, well, going to be fun and tedious at the same time? I don't know, depending on tedious, I think I'll go for. Tedious calculation to like do this expansion and check that you get exactly all of the terms you would get.
Is there a good reason for that? That doesn't require you to do the calculation?
Yeah, so the reason is it's kind of easy to see that this guy, or that this BV action has to satisfy the classical master equation. It turns out that using some standard homological algebra, the classical master equation is equivalent to showing that Form's tensor G is a DG-Lie algebra with a pairing. And once you know it satisfies the classical master equation, you can and that it's like linear on the antifields, you can convince yourself that's the only possibility.
You can also do this in like the AKSN formalism, where that you can do it that way. You follow that construction, you end up with an action like it's exactly that. And you can do the same thing with the Poisson sigma model, where the BV action is like the same action, but with these.
Yeah, absolutely right. Yeah, absolutely. Yeah, you would say like the target is G shifted by 1 with this ultimate pairing. Absolutely. So we want to ask, we're going to check that this satisfies the classical master equation. Of course, it has to because it arises from an action with gauge symmetry, or because it came from the AKSC formalism, or for whatever reason. It's quite easy to see, but I want to do it kind of explicitly so we get some feeling for it. So to do that, we need to understand what the BV antiproduct is. So that comes from a quantity I'll call the kernel. I take the delta function on the diagonal, tensored with the quadratic Casimir. But this is a 3-form with distributional coefficients on m plus m. So incorporating the various shifts and not worrying too much about the fact that it's a distribution, this lives in fields, tensor fields. So if I have two functionals of the fields, the f, e, are functions of fields, and fg is given by contracting one leg of f and one of g with this BV kernel. So I haven't said anything, really. So if we were in finite dimensions, I would have maybe chosen a basis and written out a sum. For in infinite dimensions, we try to write out the same sum, we'll find we're doing some kind of resolution of the delta function as an infinite sum.
So can you say again what this, like, what's TA?
Sorry, TA, it's standard physics notation for a basis of a semi-simple algebra.
So this thing here is that like delta function tensor with?
Yeah, sorry.
Okay, yeah. Sorry.
Delta function that I go.
Sure, I understood.
Gotcha. This is the quadratic Casimir. Now, my action functional, S, can be written as like a quadratic term plus an interacting term. And the bracket with the quadratic term, this just applies, this is a symmetry, the odd symmetry of fields by the de Rham operator. Just because the quadratic term looks like integral alpha d alpha, and if I do some contraction with the delta function, you do a little fiddling around and you see it's given by the de Rham operator. So another way to say this is the standard way, if I have in ordinary symplectic geometry quadratic Hamiltonians and linear symmetries are the same thing. If I have a linear symmetry, I get a quadratic Hamiltonian by a formula like this. So this bracket being 0 is equivalent to the de Rham operator squaring to 0. So let's look at the other terms. So we want that these guys equal to 0. We want to check that these terms are equal to 0 too. So let's first look at this term. So it just involves, if I expand alpha as a sum, alpha A answer EA, this will be alpha A wedge alpha B wedge alpha C times FAC. So because the quadratic guy just generates the action of the de Rham operator, so when we're analyzing this, we're asking, what happens when I vary this guy by varying alpha, by adding on a d of something? So I of alpha plus epsilon of this is equal to I of alpha plus epsilon. So I am looking at the derivative of this functional with respect to the symmetry given by the de Rham operator. And that's clearly equal to 0 by Stokes' theorem. Because I'm putting a de Rham operator there and there, the signs work out so that it's a de Rham operator just in front of it.
I mean, it's equal to I of alpha.
Yeah. Thank you. So the way I would think about this is, so it's some kind of vertex like that. And the key point is that integral alpha wedge beta wedge gamma from forms on M tends to Q3 or this is a cochain map. That's why this holds. So what about the next term? So let's see what that looks like. So I'm going to put in an edge in the middle, which is a delta function. And then some Lie algebra indices scattered around like that. So I brackets I is going to be a quartic function. Goes the sum. It's the integral of over 2 copies of M alpha. So on 1 copy of M, we're going to have alpha A wedge alpha B x. On the other copy of M, we're going to have alpha C wedge alpha D of x prime. And then because the thing we're sticking in the middle is the BV kernel, we're going to have a delta function x equals x prime. And then we're going to have the Lie algebra factors. The Lie algebra factors are f, a, b, e, f, c, d, e from the 2 vertices. Make sense, everybody? So this is the integral over M. Like because of the delta function, we only integrate over 1 copy of M. Alpha A, alpha B, wedge alpha C, wedge alpha D, F, A, B, E, F, C, D, E. And we know that this is graded antisymmetric. So by the Jacobi identity, this is equal to 0. So because, this tensor here is graded antisymmetric in those 4 indices, that tells us that we're only picking up the antisymmetrization of this, which is 0 by the Jacobi identity. Okay? Any questions? So I want to do one more thing and then I'll stop. So the next thing is, so we can see pretty explicitly that the classical master equation holds just by writing down these intervals. So what about the quantum master equation? So let's check. So it does the BV Laplacian apply to I vanish. So we'll write out the formula for this and we'll see that we will run into trouble. So the BV Laplacian for I is given by a diagram like this, where I've put the BV kernel on these here. So what we get is the integral over M of alpha a of x times the delta function x is equal to x times a Lie algebra factor, which is FA B. So this is a slightly funny thing. It's a product of two things, one of which is 0 and one of which is infinity. This guy is the multiplication of the delta function with itself. Or like we're evaluating the delta function at a point where it's infinity. So this is just an ill-defined expression. Question? Yep. So what we're going to try to do next time is to regularize this ill-defined expression, and by using the techniques we introduced in the first course. And what some people like to do is to say, I don't care about that part, this is 0. I don't like that. I don't know. So we'll stop there.